Alright, quick wrap up here of what I've been up to with the retro computing. So biggest thing is I got the Putty P100. It's badly fisheyed on this lens, but you know, it's a beautiful replica of the PDP-1170. Comes as a kit, pretty fun to put together. It took me several hours, burned out a couple of LEDs. Also melted one of the switches by overheating it, but I was able to repair that in software. And so you can go ahead and run the software. This starts the simulation, brings the unit up, and it shows a blinking light pattern. And depending on how you set the switches, it will do different things when you wire it up. So if I set the switches to 1002, which it says is blinky, so there's a 1002, and then if I just push this address button in, it will go ahead and get ready to reboot. I can run that and it'll bring up a different program. This is blinky, so it's a hello world with, you know, different versions of blinking lights, and you can control how it acts, make it blink faster and slower and so on and so forth. So that's a fun little demo. And then I can hit Control E at any point and just you know, stop the program from running. And I can say reset, and that will reset the program status word to 0 and the PC to 0 and so on and so forth. So this is a fully functional front panel. I can put in a 0 and say load address, and then say examine and see the contents of location 0 is a 0. I can also come to the console and examine 0 through 10. So the next location should have a 776. If I hit examine again, I will see well, a 342. Oh, I'm at the wrong address. Okay, so let me go back to location 0 and say examine. So that's location 0. There's the next location. There's 776. Next location should be 670. So address 4, 670. And then at address 6, I see a 341. That's address 6 right here, and so on. And I could do something like, you know, take a 55 and say deposit, and that will deposit a 55 into that location. And now if I say examine examine 0 through 10, where did I put my, oh, my address changed. So I'll load in address 0 and I'll put in a 55 and say deposit. You have to flip up to deposit, and now if I examine, see, it made the instruction for deposit 055, and I examine 0, it's got 55 in there. So I can fully program this through the front panel, and you know, before you had a Raspberry Pi powering this in the front panel interface, you would toggle in a basic absolute loader, something that would let you start a paper tape reader, for example, which would pull in a physical paper tape and read each line from that tape and copy it into successive locations in memory, and that would load in a more sophisticated loader, which you would then run to maybe boot from a floppy drive, or might just directly load in you know, your Fortran compiler or whatever it is that you're trying to run. So this is a nice simulation of that system. So if I go back to some of the stuff from the earlier videos, remember I had a prime number generator that you could put in an initial number on the front panel switches, and when it runs it will find the next prime and then halt with that next prime displayed on the output, and so on. So I've copied that program over to the Raspberry Pi inside this unit. It's called prime.mac. It's already been assembled and linked into prime.tape. It's a tape image, so I can say reset, and then I can say load prime.tape, and it loads in the prime number program. So if I look at location 1000, so I can put in a 1000 load address and examine, I can see what's stored in each of these locations. But I have to look over here on the data path. Okay, so load in 1000. That's the contents of register 1000. And if I say examine 1000 through 1010, I can see that I've got 12706 followed by 600 followed by 16767. So if I load this in, there's my 1276 followed by 600 followed by 16767, and so on. So if I set my PC to 1000, and the way this works, you put an initial value into the switches, and I turn this knob to say let's look at this knob over here to say let's look at the display register, and now I can say continue, and there's my first prime number is 3. If I say continue, there's 5, there's 7, there's 11, 13, 17, 19, 23, 29, 31, and then 37, and so on. So so it works, right? It's a fully functional system. So that's fun. But it's more fun to play around. That's bare metal stuff is great fun, but it's also fun to play around with some of the operating system stuff, right? So you can download from the Obsolescence website all of the images for a number of old systems that used to be available under on the PDP-11. So let me go ahead and reset this system, and we'll bring up a menu here, and these are the systems that are currently available. You can get other ones, and each of these is just a directory with some images of the drives that had the operating system or code on it. So let's go ahead and play with RSX11. This is the main thing I've been playing with. So let me toggle in a 1, right, because it's at index 1. Let me toggle in a 1 and reset the system, and this will boot up an RSX11 system. So it wants to know the time. It's probably worth putting in real information here. And this takes a little bit of time, but not too bad. So it's installing different tasks, it's attaching devices, it's doing all kinds of configuration. And that regular blinking pattern we see right now, that's the system you get when this is normally working. I'm not going to bother with LAT, and I'm not going to bother with TCP/IP. So I'm up and running, and I can say dir and see what's out there. I can say who. I'm logged in as a mystery user. I can show my memory and all kinds of things. But I'm going to log out, and I'm going to log in as myself. So I'm going to log in as user Nick, and there's my login information. And I've been doing a bit of work. I've got a few files out here, mostly related to playing around with the PIG bus, the extension of the Unibus. So there's currently no device called PG, but working off some sample code on turning the BMP-180 pressure and temperature sensor into a device, I was able to replicate that along with the I/O guide to writing an I/O device manual, and I was able to create my own device for the PIGnet. So I can look at PG drive, and this is the basic driver for the PIG bus. A lot of the stuff is just boilerplate, but basically when you initialize, you when it starts, it looks for I/O requests from the user, checks to see if we're trying to do a read or a write, and we'll jump to the appropriate place. If we're doing a read, you basically reads, you give it a offset of the register that you want to read, and it returns it to you. So get a word from the buffer that we pass to what's called a QIO, only pay attention to those 2 bits, add it to the base address, and get that word, and then hand it back to the user. So and we want to do a write, we basically get index for a register and a value, and we go ahead and we put that word into that register, and that's pretty much all there is. So that's a bit of a cumbersome way of doing interactions with the PIG bus through RSX11, but we can wrap it in software that will make it more convenient. But the driver itself is really that simple. And I'm using an old EDT editor here, which works pretty well. It's based on using a keypad, so the numeric keypad has special meaning, and we can use the 2 modes that we use in VI, for example, command mode and insert mode, that all existed, in this version of the editor. So it's a fairly sophisticated editor once you get it wired up correctly. To make it really work, we need to run Putty, because Putty, you can set it up to actually understand the keyboard of a VT100. So let me go ahead and log in here. And so, this window over here is the system console. So when system events happen, like a user logs in or logs out, we get information over here. So it's a multi-user system. So I've made some wrappers for the PIG bus. These are routines that I can call from BASIC. For connecting to the PIG bus, I give it a logical unit number, usually 1, and then I can ask for the 4 registers, command status register, data auxiliary, and slot. I can load values into those, and I also have some code that will let me wait for certain bits to get set or cleared. And these are just wrappers around the QIO functions that ultimately do the read and write. So down here, when you want to actually do a read, you basically load up to read, you take the offset that you want to go from the base register, the CSR, put that into the beginning of this 4-byte buffer, call a QIO with a read logical block operator, and it will talk to the driver, get that word from that register, put it into the high word of the buffer, and then we go ahead and make sure it worked correctly, check the IO status block, and then take that second word of the buffer, move it into R2, and return. And if it's in R2, that's where the user will pick up the value. So this is all a nice wrapper, and it's got some error checking, and it can print out error messages if something goes wrong. So it's a little bit more robust than the first versions. I learned a lot about command line interactions, using indirect files, using the macro command to assemble, using the task builder to link, how to build things in BASIC, and so on and so forth. So I've been writing tons of scripts to help me. So for example, the M command is how I can macro program assembly language. So I can either say add M and put in the name of a file, or I can just say add M and it'll ask me for the name of the file. And this is the command for assembling it, and it turns it into an object which can then be linked by using the task builder and can then be run. So I can say add M and it'll ask me, and I can say mac test, or I can say add M Mac test, and it'll run it directly. There's no command line recall that I've been able to find, and I've been thinking about how to put that together on the system, but it's hard because the simulator is reading things in character by character. So I could put a wrapper around it and pick up those characters, and when you hit and enter, save it as a line and then recall it. But when you're in the editor, for example, you have to use the arrow keys to move around, and that would conflict with a command line recall. So I've been trying to figure out if there's a good way to do that. But I've got you know, a way to assemble programs, and then I've got a way to work with BASIC. And so this is where I've been spending most of my time. BASIC is, you know, it's a basic language. We used to make fun of it, but it's actually pretty powerful. In the version of BASIC, it's BASIC +2, running under RSX. It's fairly powerful, and I thought it would be fun to be able to do interactions with this pig bus through BASIC. So that's the quest I've been on for a little while now. So yeah, this script, you know, again, I can specify file name on the command line, or I can be prompted for it, and then I'll go ahead and compile it. That's what the BASIC command does. And if that succeeds, if it doesn't succeed, it will error out. Otherwise, I can go ahead and link it, and if that succeeds, I'll go ahead and run it. And so I can play around with the pig bus like this. So we can also, you know, just run a plain old telnet session, and if we go to port 10,001, we can connect over here and have other sessions running. And you know, if I mess up the password, I'll get a console message saying login failure, and so on. And that 10,001, that's just, let me go back to the simulator. If I look at the DZ device, it tells me it's attached to 10,001. So I can attach DZ and put in a port number, and then I can communicate with it through telnet. So, you know, this is all frozen right now because the simulator has stopped. But I can continue, and everything continues the way it was. I don't know how long I can stop it before something panics when it starts and notices that time passed. But it's pretty flexible. So so what can we do with this? Well, I can open up another window, and I'll just hop onto the PyDP, and let's go into our work directory, and let me get rid of all of this stuff. So this directory is empty right now. So some sample programs I've been making. So here's a file test program. Yeah, we don't have VI on here. So here's a file test program to see if the files device actually works. I'll ask for a file name. I'll open it up. If anything goes wrong, I'll error out of the program. That's what the on error does. I'll append a path to the beginning of it, home py work. That's this directory over here. And remember, the file device opens up files on your underlying system, right? It's a pig bus device, so it's a process running under Unix. So I'll connect to the pig bus, and if anything goes wrong, I'll put an error message and be done. And then I'll go ahead and put device 1 into slot 2. So if I look at my device list, file 1 is device 1 is the files process. Device 6 is the bash process. Device 11 is the adder process. Those are the ones we're going to play with. We go back to our work area. So I'll go ahead and put the file device into slot 2, and then I'll say I want a request to read, a request to write on file 1. I'll wait until that bit turns off. So Z wait waits till a bit goes to 0. And then I pump in the file name one character at a time. So I just loop over the whole path, get out the ASCII code of each character, put it into the data register, and then I set the CSR register to say request to write, and I wait until that bit 7 goes low, and that tells me it's processed that character. And then when I'm done, I put a 0 in and do one more request to write. That concludes the transfer of the file name, and it should open that file for writing. And then I read line by line from the file that I specified in the beginning. And for each line, I do the same thing. I go through each character, put it into the data register, put a 21. That's a request to write. So 201 is a request to open a file for writing. Here I'm actually writing individual characters. So I put a 21 in the control register, wait for that bit 4 to go low, and print out a dot just to let me know that it's doing something. I don't put out a new line at the end. I decided to just let it read the carriage return, character 13 from the file, and put that in. And I just go back up here, read another line, and keep going. When I hit the end of the file, I'll get an error. I'll come down to EOF, and I'll come down here, put a 401 into the CSR, which says close, file ID 1, wait for that bit to go low, and we're all done. What does all that mean? So I can build this. So build file test. It'll compile it, it will link it, and the linking takes a little while, and then it'll go ahead and run it and ask me for a name. Well, how about file test.b2s? And I got an error assigning PG to logical unit number 2 because PG doesn't exist. So one time after I boot, I have to run A3, and then I can look at device PG : and it's loaded. So now I can run file test, and I can say file test.b2s, and it goes ahead and pumps it in. And if I look down here, I've got a file test.b2s, and that's the program that I just specified up here. And it's got control M's on the end because that's what RSX11 used. So I can run this again, and I don't know, we'll do Mac drive or big drive .mac, and we can do big drive or bigtable .mac, and let's go ahead and do pig.io .mac, and then pig.io.include, and that's pretty much all the stuff that I've been building to do this interchange. So I basically include pig.io that sets up these calls like put slot and zwait and put data and put CSR and so on. And they're just declarations, and then the zwait and the nzwait are just short little basic functions. So so yeah, the system works, and if I do a PS, I can see I have a process files running. That's the virtual device sitting in the slot of the pig bus. So so that all works. Now you can also set up FTP connections. If I try to do FTP right now, IFC doesn't work. So when I booted this up, I told it not to load TCP/IP. So let me shut down the system. And that'll take a minute. And then I'm going to go ahead and I'm going to reboot, but I'm going to install RSX11 their TCP/IP processes. One wrinkle on this is that to do TCP/IP, this underlying simulator has to run as root. There may be ways around that, but I haven't found one easily, so I'm just going to go ahead and do this as root. So let me come over here and quit, and I've made a little script called priv, and priv will say PyDP is currently set to run as Pi, would you like to run it as root? And I'll say yes. And so now, you know, this executable links to the privileged version of realcons. So now if I run PDP, and my switch is still set to 1, so it should still boot up RSX11, and it should come up with TCP/IP enabled. So I'm not going to worry about the date and time here. And I will skip lap, but I will load TCP/IP. So I'll skip that, I'll load TCP/IP, and so that's up and running. And I'll go ahead and root. Well, let me log out. And I set it up so that when I log in, it runs this IFC command and it shows me what the address is. So from here, I can ping Google, which is great. From my desktop system, I can telnet, or I can telnet 192.168.0.167, and you know, get access to the PDP-11. But I can also FTP, so FTP 192.168.0.167, and I can log in. And now I got an FTP process running, so I can say ls, and I can see all the files sitting over there, and I could get, you know, bigwrite.mac, and it pulls it over into my current directory. So that's a pretty straightforward way of doing I/O to get files onto and off of the system, but I wanted to try to do it with the pig bus anyway, which was that previous work I was showing you. But you can set up networking like this. Like I say, the only sort of wrinkle is so far it seems like we need to be running the PyDP code as root. So if I look over here, I can see that the client 11 is running as root. I don't think there's any real downside to that. This is all, you know, behind a firewall, and obviously, you know, telnet FTP are not encrypted, so I wouldn't want to be doing this over an open connection anyway. But I can still choose to disable this and say, let's go ahead and run this as just the Pi user. And I should probably get rid of the Pi account anyway, because that's a little bit of a vulnerability. So let me go ahead and rerun this, and we'll bring up RSX11 again and see what else there is in there. This was probably about 15 hours a day for, you know, about 2 weeks of working on the hardware side, working on the software side, learning tools. There's lots of documentation available, particularly for RSX11, and a lot of it is not searchable. So if you want to know about I/O programming, you can come in here. It's just scanned, it's not OCR'd and so on. So you get very good at using the table of contents and using the index. And, you know, unfortunately, page 2-60, how do you know what page that's on? Well, I don't know. So you come down and you find 246. Okay, so I need to go up another 14 pages. So I'll go to 147, and that gets me pretty close to page 2-60. Alright, so I'm up and running. I didn't answer the questions about TCP/IP, so but even if it tries to install TCP/IP, it will fail because it's not running as root. So if I do my PS, everything's running as user pi, and somewhere way back here, pretty close to the beginning, it tries to install the networking device, and it will get an error message. So this is where we started booting, and it tries to install XU, and it says not attached. If I try to do this, it tells me you don't have permission to perform capture on that device. So that's why you need to be running as root. So yeah, 150 plus hours messing around with this stuff. At some point, decided I needed to touch Earth. So some of the other things, so there's the wooden base that comes with this, so you can stain that and put feet on it and such. I also wanted to be able to interface without running cables through holes, so had an old Ethernet port that I was able to wire up to and make that as a plug-in. Power port up here, and then took the I2C wires, power and ground, and the one unused GPIO 19, and I farmed that out through just a set of points where I can put wires into, or a connector. So I have access to an I2C bus, and then I have an LCD display, and 3D printed a holder for it, and I can hook that up as follows. So I think I color coded it correctly, so yellow goes to yellow and brown goes to brown. That's VCC. Orange to orange, and this is just a little 4x20 LCD display. And I printed this case so that it sits inside here, and this can attach to the back of the Pi DP. Alright, so that sits up there. There's a connector in the back that you hook up to turn on the backlight. It's badly focused. If you short that out, the light's really bright, so I put in a variable and measured it out, and about 220 ohms is a nice intensity, and then you can adjust the contrast. So I went ahead and wrote some code for that. Also in BASIC. So and there's an LCD device. So here's the LCD device, 20x4 driver, and real simple CSR. Initialize with bit 1, choose a line with bit 2, and when you turn on bit 2, you put the line number 0 through 3 in the data register. When you want to send a character, put it in the data register and turn on a 4 for the CSR. When you want to clear the display, put an 8 in the CSR. And if you get an error, CSR will turn on bit 15. So these are just some bit masks for checking the conditions. And then this is the driver, right? So I wait until I get a ping from the simulator, and I check to see if it's an init or a clear or a line or a send, and I update accordingly. And before I do anything, I Oh yeah, no, that's the main loop, so I don't have to do any initialization. And this is all this is all code that I just ripped off from someone else and then bundled into a library. So this is Lewis Laughlin's code, and I just put it into a library with a .h file and a callable file. And basically the ability to do the initialization, to type a character, and to select a line. And so that's pretty much a slam dunk. So if I come back into the basic program, same thing that we were seeing with the file test program. Do your initialization by including pig.io.inc. Here's my subroutine for printing a line, and it basically for choosing a line, so it prints a line with a certain message starting at a certain line. So I take that line, put it in the data register, turn on bit 1, right, a 2 in the CSR, that sets the line, wait for bit 2 to go off, and then loop through each character of the message, put it in the data register, put a 4 into CSR, wait for that to go off, and that sends the string into the LCD. So when you start this program, come back in. When you start this program, we call pig initialize, attach it to logical unit 1. The LCD was device 11, so I put a B01, but let me put it into slot 2 because we got the files device in slot 1, and then initialize it, and then I just print out some messages. So let's go ahead and run that. 6 character limit on file names. Big bus init failure, so why is that? Because you did not load the device. So let me load the device and then run the LCD test, and let's watch the display. I don't know how well this will do brightness wise, and there's our message. Hello, the time is, and the smiley face at the bottom. So we can totally interact with PigBus devices, which is cool. And then just because it was the last day of winter break and I was feeling ambitious, I decided to try using the bash device. So, and again, this is all running from basic, right? So here's the bash device. So initialize the PigBus as logical unit number 1. Put device 6, that's bash, into, we're actually going into slot 4, not slot 3. And then get a command from the user, add a new line at the end because bash needs that new line to do anything, and then loop through as usual, pump it out to the bash device 1 character at a time. So do the request to send, wait for it to go off, and then I don't have interrupts working, so I did the next best thing. I just poll. I'll poll 64 times in a row to see if there's a character coming in. If there's not, I give up and go back and get another command from the user. But if I get a character in here, I'll do a request to read, wait for the request to read to be acknowledged, and then check to see if there's data available. If there's not, if there is, I'll go down here to got a character. Otherwise, I'll go back and loop, do that 64 times. If after 64 times no characters came in, I go back and get another command. So unless there's a command that takes a while to generate output, this will pick up the output after the command. When I get a character, I pull it from the data register, change it into a string, print it out with a semicolon to say don't do a new line. And if it's a new line character, ASCII character 10, I go ahead and put a carriage return as well, so it comes back to column 1, and then I go back up to the top and try to read. So this loop just keeps scanning for input, and when there's no more input available, I'll come back up here and get another command. And this actually seems to work, so I can say pwd, oh, I'm uppercase now. Well, that's not going to work because it's all uppercase stuff. So let me come in through Putty. So I'm going to run bash and do a pwd. There's my directory. There's an ls. There's a date. I can switch directories and do an ls. I can look at my bash rc. And I mean, I'm running bash through a basic program on an RSX 11 system running on an emulated PDP 1170 from the mid 70s. That's some crazy layers of indirection and so on. But this all seems to work. So yeah, that's a little bit about what I've been up to. Yeah, so I want to try to get interrupts working. That's a longer term goal. I need to clean up some of the documentation on all of this, and I want to push it back out to the latest GitLab release. I changed a bunch of things after the initial release, got some really good feedback from people on the PyDP group. And I switched from 3 registers to 4. I put the CSR at the base instead of base plus 2. I tweaked the meaning of the bits in the CSR for a couple of devices, the adder and the alarm, but then I decided since this is all just proof of concept, I would just stick with the quirky order that I had. But yeah, just interesting things to play around with. And not sure where it's going from here. I spent a while playing around with a cassette tape recorder and trying to make a system for storing and retrieving files using tones on a tape. I was able to get that work using dual tone multiple frequency coding like you have for push button telephones, but very slow, a few characters per second at the most, but it worked. But the recorder I'm using is not terribly high quality, so I tried doing things at a higher speed, and it broke down pretty quickly. But anyway, that was an interesting sidetrack, and yeah, not sure where it's going after this. Maybe custom operating system, maybe custom compiler, probably more devices, and not sure what else. I'd like to do a GPIO expander. I already have that device written, and it works when I just hook it up bare hand, but being able to plug it into the back like the LCD panel and farm that out somewhere would be pretty fun. So anyway, that's some of what I've been up to. Highly recommend this system. It's a lot of fun, a lot of interesting things to get into. Alright, thanks. Bye.